Okay, so last class we discussed basic idea of force. Okay, then some common forces that we come across in daily life. One force we discussed in detail was weight of an object. The formula for calculating weight of an object is W is equal to mg. M is mass of the object, g is acceleration due to gravity, weight acts in the vertically downward direction. And the other forces we talked about were friction, normal force, which is basically any pushing force which involves contact. Okay, that is normal force. And then tension, which is basically a pulling force which involves contact. Okay, so whenever an object has a tendency of getting stretched, internal forces develop inside the object. They help in maintaining the shape of the object. That force is what we call as tension. Next, we talked about inertia. When objects are at rest, mass is a measure of inertia. Greater the mass, more difficult it is to bring the object into motion. Right? And when objects are moving, the last point we discussed was that momentum is the measure of inertia of motion. So we'll talk about momentum in detail and then impulse. Okay. Denoted by the symbol P, it's a vector quantity. Now, suppose there is a particle. Okay, we are talking about a single particle of mass m moving with a velocity v. Then its momentum is calculated as P is equal to mv. This is the basic formula for momentum. Okay, so if the mass m moves with a velocity v, then its momentum P is equal to mv. Now we know velocity is a vector quantity, it has a direction, and mass of an object is always positive. So when you multiply mass and velocity, you are multiplying a positive number with velocity. Then the direction of momentum and the direction of velocity will be the same. Okay, so momentum is in the same direction as velocity. Right. Quickly tell me the SI unit and dimensional formula of momentum, both of you. SI unit and dimensional formula of momentum.
kg meter per second.
Okay, it's simply mass multiplied with velocity. So the unit will be SI unit of mass multiplied with SI unit of velocity, kg meter per second. Vanilla, what is the dimensional formula?
ml t power minus 1.
Okay. Kg is mass, meter is length per second. So ml t power minus 1. Correct. Fine. Now see, this formula P is equal to mv can be used when you are sure that the entire mass m moves with the same velocity v. It's quite possible that different parts of a system move with different velocities. Okay. For example, you can consider a person itself as a system. Okay. If you take a person as a system, it's not necessary that every part of the person moves in the same manner. For example, I am moving my hands, but my entire body is not moving in the same way in which my hands are moving, right? So it's quite possible that different parts of a system move with different velocities. In that case, the momentum of an entire system can be calculated as first mass multiplied with the velocity of the first mass, second mass multiplied with the velocity of second mass, and so on. Nth mass multiplied with velocity of the nth mass. You will have to add momentum of individual particles of the system to get the total momentum of the system. Okay. But in this chapter, we will mostly come across situations where the entire object moves with one velocity itself. Okay, so you mostly will be using the formula P is equal to mv, but it is possible that systems have different parts moving with different velocities. Then you'll have to calculate momentum this way. Okay, let's quickly solve one question. Consider two particles. Let's say A's mass is 2 kg, B's mass is 1 kg. Assume A is moving to the right with a velocity of say 4 meters per second, and B is moving say downwards with a velocity of some 6 meters per second. Okay. Calculate, okay, A and B individual momentum, it's quite easy for you to find out. Calculate the net momentum of this system. Do this quickly. The formula for momentum of a particle is P is equal to mv. Use that and find out the total momentum of this system. Any answer? Okay, Pawan, you tell me, what are the steps to take?
Sir, first we have to find out the momentum of A and B.
Okay, so momentum of the total system will be momentum of A plus momentum of B. Correct. How much is A's momentum?
Sir, 8
2 into 4 is 8. Tell along with the units. Okay, kg meter per second.
kg meter per second.
How much is B's momentum?
6 kg meter per second.
6 kg meter per second. Then what is the total momentum? Can we say
14 kg
14?
meter per second.
Okay, you're saying 14. Fine. Vanilla, do you agree with this answer?
So we should consider its direction also.
Okay. The bar is very important. Momentum is a vector quantity. Pawan, can you simply add vectors like numbers?
No, sir.
Okay. Then you tell me any idea how to add these two and get the total momentum of the system.
Sir, by keeping cap.
Okay. Don't say by keeping cap. Say by expressing them as vectors or by writing them in mathematical form. Correct. Okay. So tell me, how do you express A's momentum as a vector? It is directed to the right. So how to write it as a vector?
8 I cap.
8 I cap, correct. So if you make it a vector, you'll have to write 8 I cap kg meter per second. And B's momentum?
Minus 6 J cap kg meter per second.
Right, minus 6 J cap. So the net momentum of this system becomes 8 I cap minus 6 J cap kg meters per second. You can even find out its magnitude. Magnitude of the total momentum of the system. Vanilla, tell me how to calculate the magnitude of this vector.
Root 6 square plus 8 squares.
Root of 8 square plus 6 square becomes?
10, sir.
10 kg meter per second is the net momentum of this system. It's not 14. Okay, fine. So just keep in mind that vector momentum is a vector quantity, not just in this question. Any physics question, if you are dealing with vector quantities, you have to use the procedure meant for vector quantities. Okay, fine. Another question. Let's include some ideas from circular motion in this. Let's say there is an object. Assume its mass is 2 kg and it moves with a constant speed of say 10 meters per second, and radius of the circular track, let's say, is 4 meters. Okay. Or let's take it as 4 by pi meters. Just a moment. Fine. 40 by pi meters. That's the radius of the circular track. So I want you to find out, like, this is the initial position. What is shown to you here, A, is the initial position of the object, and you can assume it is moving this way, anti-clockwise. I want you to calculate the change in momentum of the object in, let's say, 2 seconds. Okay, yeah. Calculate change in momentum of the object in 2 seconds. So one of you tell me the steps that you will have to take to answer this.
Sir, we have to find out the velocity at 2 seconds.
We'll have to find its velocity after 2 seconds. How to do that? See, I told you the object is moving with a constant speed. Speed is constant, but since it's moving in a circle, direction keeps on changing, so velocity changes. But we know the speed, means we know the magnitude of velocity. What is the only thing unknown? If you want to calculate momentum, you need velocity. Velocity is a vector quantity, and we already know its magnitude. What else is to be found? What all?
Distance, sir.
Okay, what will you do with the distance? Okay, see, just think step by step. You are asked to calculate change in momentum. Tell me, what is the basic formula for change in any quantity? Basic formula for change in any quantity.
Final momentum minus initial momentum.
Final value of the quantity minus initial. So final momentum minus initial momentum. Okay. Initial momentum is quite easy to express. We know its mass and we know its initial velocity. We can do that. So we need final momentum. Basically, what you need now is mass multiplied with final velocity. That is final momentum minus mass multiplied with initial velocity. That is initial momentum. Initial velocity is known. Mass is known. What we now need is final velocity. And in final velocity, we already know the speed. Velocity is a vector quantity. You know speed means you know the magnitude of the vector. What else is to be calculated? What all does a vector quantity have in general?
Magnitude and direction, sir.
Magnitude and direction. Velocity is magnitude is speed. We already know that. The only thing unknown is the direction of velocity. So after 2 seconds, you should find out which way the object will be moving. So if you know where the object is, okay, since the object is executing circular motion, if you simply know its position, either here or here, you can tell the direction of its velocity. If it's here, the direction of its velocity is like this. If it's here, the direction is like this. We'll do some calculations and get the angle. Okay. So you need to find out where the object will be after 2 seconds. How to do that? Vanilla was saying distance. Okay. How much distance will it cover in 2 seconds? You know the speed with which it is moving, you know the time 2 seconds, how much distance will it cover?
20 meters.
20 meters. But by knowing that distance 20 meters, how are you going to tell at which angle the velocity is moving? At which angle the particle is moving? Or if you have any other ideas, you can share. Pawan, you also.
So theta equal to L by R.
Good, good. That is a valid idea. Okay, L is equal to R theta, theta is equal to L by R. So you are saying we'll find out the distance that it moves and divide that by the radius, we'll get the angle. That is correct. It works. Okay, fine. Let us do it that way. Theta is equal to L by R. Or let's first find out, like from speed and time, we can say that the distance it is going to cover is speed into time, that is 20 meters. And L is equal to R theta. So theta becomes L by R. So the angle it rotates becomes 20 divided by R is 40 by pi, becomes pi by 2 radians. Pi by 2 radians is how many degrees?
90 degrees.
90 degrees. That means the particle after 2 seconds would be here at the topmost position. If it is there, it's easy to find out, or it's easy to express its velocity. This is the final velocity of the object, particle. Okay, let us complete this problem now. Or you only do this. You know how it was moving initially, you know how it is moving finally. Substitute all the quantities there and tell me the total change in momentum as a vector. Do this, both of you. Okay, any answer? Fine. Pawan, tell me the final velocity of the particle as a vector. You know it is moving to the left. You know its speed also. So tell me its velocity as a vector.
Sir, minus 10 I cap.
Minus 10 I cap. Fine. Mass is 2 kg. So 2 into final velocity is minus 10 I cap minus initial velocity. How do you write that as a vector?
Sir, plus 10 J cap.
10 J cap. That's all. That will be the change in momentum. You can put the minus 20 outside. It will be I cap plus J cap meters per second or kg meters per second. You can even express its magnitude if you want. Magnitude of change in momentum will be 20 root of I cap. Okay, I cap plus J cap. Its magnitude is root of 1 square plus 1 square. That is root 2 kg meter per second. That is change in momentum. Fine. So from now onwards, we'll keep solving multi-conceptual questions like this. Usually in your final exam, final entrance exams, they'll be asking multi-conceptual questions itself. You'll have to think of multiple steps to arrive at the answer. Okay, fine. Another question. Suppose the object's mass is some 4 kg. Its initial velocity, or let's take it like this. Let's include motion under gravity now. Assume the object is projected vertically upward. With a speed of some 40 meters per second. Okay. We'll only consider gravity, we'll ignore air resistance. If an object is projected upward with a speed 40 meters per second, what is its time of flight? Do you
That's
remember?
4,
Yeah, tell me.
4 seconds.
What
8
formula?
seconds.
4 or 8?
8, sir. 8, sir.
8 seconds. Time of flight is 2u by g. Okay. So in 8 seconds, it comes back to the ground. Before it comes back to the ground, it's only under the influence of gravity. Then we can tell anything about the object. So what I want you all to calculate is, first thing, change in momentum in, okay, 3 seconds. Next thing, okay, 3 seconds after projection. Okay. What is its momentum at 5 seconds? So this is a case of motion under gravity in one dimension. Equations of kinematics are applicable. Okay. Acceleration due to gravity is constant. Okay. Solve this quickly. Okay. Any answer?
Minus 120 Jacob.
Okay. First part you are saying is minus 120 J cap. Fine. How did you calculate that?
Sir, I calculated velocity at 3 seconds.
Okay, good. Mass is known, initial velocity is known. All we need is final velocity so that we can tell final momentum minus initial momentum. So you'll have to calculate velocity at 3 seconds. Which equation did you use for that?
V equal to U plus 8.
Okay. U is 40. Acceleration, how much did you take?
Minus 10 meter per second.
Minus 10 into 3. Okay, fine. So velocity becomes 10 meters per second, and then we can tell the change in momentum. Mass is 4 kg into final velocity minus initial velocity. Minus 30 into 4 becomes minus 120 J cap kg meters per second. Is the change in momentum. Pawan, is this clear?
Yes, sir.
Right. Next, Pawan, do you have an answer for momentum at 5 seconds? Tell me its velocity at 5 seconds quickly.
Sir, downward 50 meters per second.
Downwards, how much?
Sir. 10 meters per second, sir.
10 meter per second downwards. Correct. Again, V is equal to U plus 80. You will get the velocity as minus 10 meters per second. Okay. And then you can tell its momentum is minus 4 into 10, minus 40 kg meter per second j cap. Okay, Vanilla, is this clear?
Yes, sir.
Okay. Right. So basically that is how you calculate momentum, changes in momentum. Keep in mind that momentum is a vector quantity. Okay, direction is very important. Next, impulse. This is another physical quantity, but like we all already have some idea about this. Have you ever heard this term impulse? Not in physics, but outside. Any of you?
No, sir.
No. Okay. Have you ever heard something like impulsive decisions, impulsive actions? No? Okay. And an impulsive decision is like a sudden decision. Okay. Like you get a signal from somewhere and you quickly decide to do something. Okay, that's called an impulsive decision. Now in physics, okay, impulse is basically a sudden change in momentum. So effectively, impulse as a quantity is just change in momentum. But why are we giving it a separate name? If it happens quickly, if it causes a sudden change in the motion of an object, then we call it impulse. Okay. Can one of you tell me any example of an object whose motion suddenly changes? I'm not saying its motion should change all by itself. There can be an external agent making it change, creating disturbance. But just tell me any example of an object whose motion suddenly changes. Suddenly means within fraction of seconds. Yeah, before it must have been moving with some velocity, and within fraction of a second, its velocity suddenly changes to something else. Can you think of examples like that?
Sir, mosquito.
Okay, fine. Yeah. Uh, a housefly would be a better example. Yes. Suddenly, like they change direction of motion very quickly. Yeah, fine. You can call that. You can call that change in momentum as an impulse. Any other examples? Fine. See, usually in collisions, you will come across impulse. You will come across sudden changes in motion of objects. For example, let's say you drop a ball onto the floor from a certain height. Okay. Now, till it hits the floor, it will be moving smoothly only. Like its velocity is not constant. It will change. Okay. It will undergo change in momentum as it falls down, because initially its velocity is 0. But after some time, its velocity could become like 1 meter per second. After some more time, it may become like 5 meters per second. Okay. And ultimately, it hits the ground at one moment, at one instant. Let's say it hits the ground with a velocity of some 7 meters per second, just as an example. Then what happens after it hits the ground? Immediately its velocity changes. It's not a gradual change, it's a sudden change. Okay. Just after hitting the ground, its velocity could suddenly change to something like 6 meters per second in the upward direction. Then again, it gradually decreases, maybe becomes 2 meters per second somewhere, and then comes to rest somewhere here. Okay. So see this 0 to 1 and then this 1 to 5, these are gradual changes. Okay. There also there is change in momentum happening. Velocity is changing, momentum is changing because mass is constant. But you don't call that change in momentum as impulse. Fine. You look at this. Just before collision, the momentum of the object, let's say the mass of the ball is some 2 kg, very heavy. Momentum just before collision, let's call it initial momentum, is 2 into 7 in the minus j cap direction. Momentum just after collision, let's call it as final momentum, is 2 into plus 6 j cap. Okay. So from minus 14, it is becoming plus 12 in a very, very short duration of time. Okay. Such sudden changes in momentum are called impulses. Fine. So usually when two objects collide, you can see an impulse there. You can see a sudden change in momentum there. Okay. Now momentum SI unit is kg meter per second. So change in momentum, that is impulse SI unit, will also be kg meter per second itself. They'll have the same units and dimensions. Okay. Let's solve one question based on this. Okay, let's say there is a ball, or okay, you think of it as a carom coin. Okay, carom coin mass maybe a few grams, let's say 20 grams. I don't think it'll be that much also, but let it be. Assume it is moving towards the edge of the carom board, initially like this, with a velocity or speed, angle I'll give you. Let's say it is moving with a speed of some 10 meters per second, making an angle 53 degrees with the edge of the carom board as shown. After collision, let's say you assume it goes like this, in this direction, with a velocity 5 meters per second only. Okay, due to collision, it may lose some energy, it may slow down at an angle 37 degrees. So I want you to calculate impulse on the coin when it strikes the edge of the carom board. Impulse by definition is change in momentum. So that is what you are required to calculate, and keep in mind that momentum is a vector quantity. Okay, any answer? And listen, you are asked to calculate impulse. Impulse by definition is change in momentum, which is mass into final velocity minus initial velocity. That's all. Mass is known 20 grams. We'll express it in kgs later. We need to write velocities as vectors, final and initial. Can one of you tell me how to write this final velocity 5 meters per second in terms of I cap, j cap? How much will its x component be?
Four I cap, sir.
The angle it makes with x-axis is 37 degrees, so it will be 4 I cap. And y component? With x-axis, if it makes 37, with y-axis, it will be making 53. How much will the component be?
3 J cap, sir.
3 j cap. That's the final velocity. So mass is 20 grams. Gram is 10 power minus 3 kg. Final velocity is 4 I cap plus 3 j cap minus initial velocity. That 10 meter per second, we'll have to express it as components. Pawan, can you tell me its x component?
Sir, 16 I cap.
Vector itself is 10. How can component be 16? Did you say 6 or 16?
Sir, 8 I cap, sir.
How did you get 8 I cap? How much angle does it make with x-axis? How much angle does it make with x-axis?
Sir, 53 degrees.
Then vector's magnitude is 10. Angle is 53 degrees. How much is the component?
Sir, in 37.
You put change your answer then.
Sir, 6 I cap.
Good. X component will be 6. What about y component?
Sir, 8 I cap. Minus 8 J cap.
Minus 8 j cap. So the final velocity will be 6 I cap minus 8 j cap meters per second. And okay, you can do the rest of the calculation. Okay. But see, this is how you calculate impulse. I'm not saying this is the only way to calculate impulse. This is one of the ways. So by definition, it is change in momentum. So you find out final momentum, initial momentum, subtract them. You'll get the impulse directly. Okay. So basically during collisions, we'll talk about impulse. And sometimes, like you said, the example of a housefly, generally, whenever you feel there is a sudden change in the motion of an object, you can talk about impulse, right? So till now, we have discussed basic ideas of these quantities like force, momentum, and impulse. We even talked about something called inertia. Let us now discuss laws of motion, okay, proposed by Newton. So we call them Newton's laws of motion. If any of you know, you can tell me what is the first law of motion? The first law, it's also called the law of inertia. Tell me, what is inertia? We had discussed this in the last class.
Sir, the object which needs an external force.
Can you repeat? Object?
Sir, object ki external force and place and change of motion there.
Okay. That's fine. That is correct only. You are telling the law of inertia. I'm just asking you what is inertia. Vanilla, can you tell what is inertia? Okay, fine. See, inertia.
Not changing state of motions.
Okay, the tendency of an object to continue in its state of motion. That is what is inertia. Correct, correct. So basically, inertia is the reluctance or reluctance of an object to change its state of motion, or the resistance of an object to change to a change in its state of motion. That is what we call as inertia. Now the law of inertia states that, or Newton's first law states, any object, okay, will continue in its present state. Okay, if it's at rest, it will continue to be at rest. If it's moving, it will continue to move like that. Okay, unless acted upon by a net external force. Okay, so let me quickly write that statement here. Objects continue in their continue to be in their present state. Okay, of it could be a state of rest or motion. Unless acted upon by a net. Net means the resultant non-zero force. Okay, by a net non-zero force. So basically what it means is that objects can only be disturbed by forces. And the reverse is also true. If there is an unbalanced force on an object, it will definitely disturb the object. Okay. So tell me, Pawan, tell me an example of an object whose state of rest or motion as observed by you is not changing.
The statue.
Statue, good example. Okay. A statue somewhere on the road. Correct. So now the law states that objects continue in their present state of rest or motion unless acted upon by a net force. Now we see that statue is continuing to be at rest. Okay, it's at rest, it continues to be at rest. What can you say about the forces acting on it? Are there any forces or there are no forces?
There are no forces acting on it.
Okay, Vanilla, what do you say? A statue is at rest, it continues to be at rest. Do you think there are forces acting on it, but still it is at rest? Or do you think there are no forces, that's why it is at rest?
Gravitational forces.
Earth's gravity will definitely be there, right? Pawan, yes or no?
Yes, sir.
Statue బరువు ఉంటుంది కదా. Then why is it continuing to be at rest even though there is a force acting on it?
Sir, it's acting vertically downwards.
Let it act. It's acting vertically downwards, that's fine. Still, why does it not move then?
Sir, in normal force in the gravitation force equal level.
There is another force also acting on it, not just the weight of the object. Correct. So just a moment, let's take this example. Right. Assume this statue is at rest. Now, any object we know has mass. Okay. So as it has mass, it will be experiencing weight. Weight is basically the gravitational pull of the earth, and it will be in the downward direction. Okay. So object will be experiencing weight downward. That is the force which the earth exerts on that object. Right. If that had been the only force acting on it, it would definitely have accelerated in that direction. Okay. But that's not the only force acting on it. It's placed on a platform. The platform exerts a normal force on it, an upward force on it. It's like that example that we discussed yesterday, holding a bottle on the palm of your hand. Earth is trying to pull the bottle down. Okay, Earth is pulling the bottle down, but your hand is pushing it up, and they are balanced. Okay, so the normal force will be acting in the upward direction, and these two are of equal magnitude but opposite direction. So it's like two vectors of same magnitude but in opposite direction. Then the net force on statue is 0. That is why its state is not changing. Okay, so there are a few things we can understand from this. If an object continues in its state of motion, it doesn't mean there are no forces acting on it. Okay, it could also mean that the net force acting on it is 0. There are forces acting on it, but their sum together becomes 0. Their net effect or resultant effect becomes 0. So if an object's state of motion is not changing, there are two possibilities. Net force could be, there may be no forces acting on it at all, or there may be forces, but their resultant is 0. Okay. Now tell me an example of a system or an object of a system or an object which is moving, but its state of motion changes. An object or system which is moving, but the way it moves should be changing. Tell me such an example. Can't you think of any object which is moving, but the way it moves changes?
Ball thrown upwards.
Ball thrown upward, correct. Okay, good. Its velocity changes. State of motion is changing. Means there must be forces involved. Now, Vanilla, you only tell what changes the state of motion of a ball that is thrown upward.
Its velocity decreases.
What causes the velocity to decrease?
Earth's gravity.
Gravity, the weight of the ball, you can say. Correct. Okay. So if motion of a system or object undergoes any change, that should happen due to forces only. Okay, there will be one or more forces behind that. Okay, now suppose you slide a block on a surface, on a rough surface. Okay, just assume there's a block on it. You slide it, means you give it some velocity, let's say some 5 meters per second, and you release. We know that after, like, as it moves forward, the block slows down. Maybe its speed becomes 3 meters per second, then 2, 1. Gradually it will come to rest. What force is responsible for the change in state of motion of this block? What force is causing the velocity of this block to change?
Frictional force.
Friction, correct. But Pawan, you tell me, do you think friction is the only force which acts on the block as it is released, like after it is released?
The gravitational force.
Its weight will definitely be acting, correct. What other forces act on it? You said friction. Yes, friction acts parallel to the surface of contact. Object is sliding to the right. So common sense, from everyday experience, we can tell the force of friction must be to the left. What other forces act on it?
The normal force.
It is pressing, it will be pushing or pressing the floor downwards. The floor will be supporting it in the upward direction. So there will be a normal force also acting on it. Correct. So under the under the influence of all these forces, its velocity finally decreases, slowly decreases. But like, see, these two forces, normal force and weight, they are vertical. Fine. but its velocity is changing in the horizontal direction. Vertically, it's not undergoing any disturbance. Horizontally, the way it moves is changing. Okay, so the horizontal force must have been responsible for it. So you said friction, which is correct. So basically, that is what Newton's first law says. And it works both ways. If an object's state of motion changes, there must be one or more forces acting on it. Okay, there must be a net force acting on it. Reverse. If there is a net force, okay, I'm repeatedly using this term net. Net means the combined effect of all forces being non-zero. Then we say there is a net force acting on it. If there is a net non-zero force acting on a system or an object, its state of motion will definitely change. Okay. And if one is not there, the other is not there. Means if state of motion is not changing, that means net force is not there. And reverse, if net force is not there, state of motion won't change. Okay. That is what the law of inertia states. No formula for it. This is just a general observation. Okay. But this is very useful for us while solving problems. Okay. Because in many physics questions, you will be asked how a particular system will be moving after some time. Okay. Or what will be its velocity after covering some distance, or what will be its momentum after covering some distance, something like that. You will have to predict the state of motion at some other instant. Now, like from everyday observation or from first law, we know that state of motion, whether it changes or not, depends on forces. Okay. So if you want to solve any mechanics question, not just mechanics, even electrostatics and all, if you want to predict the future state of a system, you will have to consider the forces acting on it, because state of motion is changed by forces. Okay, can be changed by forces. So in any physics question where you are asked to find out something about a system at a future instant, you will have to consider the forces acting on the system first. That is how first law is important to us. Okay. Second law. Anyone? Do you know the statement or the formula for Newton's second law? Okay, fine. Now see, we just discussed that forces change the state of motion of a system. And reverse, if state of motion is changing, there must be one or more forces involved. One of you tell me, how will you say, on what basis will you say whether the state of motion of a system has changed or not? Like if you slide a block on the floor and release it, we know its state of motion is going to change. On what basis are you saying that its state of motion is changing?
Its velocity changes.
By looking at its velocity. Correct. Possible. So fine, velocity changing is one indication of state of motion changing. That's fine. What about systems like, okay, let's consider this now. So just imagine a situation like this. Assume there is a surface. Let's say it's a dusty surface. There are a lot of dust particles on it. Assume there's a block which is moving in the forward direction. Let's say the initial velocity of the block is 5 meters per second. Now we know this object is going to slow down and stop. If you need to maintain that speed, fine, you will have to, okay, tell me how to make the block maintain that speed.
So if no force acts on it, it will maintain its speed.
Okay, no force. Let us remove the floor. Assume this is happening in space. There's some object floating around in space, and in space, assume there is some dust. Okay, they call it interstellar dust. Let it be. Vanilla, you tell me, suppose this object has been released from a rocket or something, and there are dust particles in front of it. What will happen to this object? The moment it was released, its speed was 5 meters per second. What will happen to it? Pawan, you can also take a guess. There are dust particles surrounding. We released an object into that cloud of dust. Don't consider gravity and all. This is in outer space. Okay. What will happen?
Sir, a block of particles కూర్చుకొని slow అవుతుంది.
As the dust accumulates on the block will slow down. Correct. Good. Good. Now, if you want to make the block maintain that speed, what can you do? Vanilla will say we'll remove the dust. But no. What else can you do? Dust is there, but object has to continue going with the same speed, same velocity. What can be done? Or what should be done? And we know that block will slow down. We have to prevent it from slowing down. What can be done or what should be done? So according to you, nothing can be done. It will have to slow down. Pawan, any ideas?
Sir,
Okay.
mass ఏమైనా reduce
What did you say?
mass ఏమైనా reduce చేస్తాం సార్.
మీరందరూ చాలా క్రేజీగా ఆలోచిస్తున్నారు. ఆమెమో బోట్ స్ట్రైట్ పోవాలంటే ఏం చేయాలంటే రివర్ ఆపేద్దామంటే ఇప్పుడు పోయి దాని మాస్ ఎట్లా హౌ విల్ వి డిక్రీజ్ ద మాస్ దేర్? Okay, anyway, decreasing mass is also not a solution. How about applying a force like this? Will it help the block maintain its speed or not?
Yes, sir.
In the absence of the force, the block would have slowed down. You can talk about daily life situations also. Like you just roll a ball on the floor, it will roll up to some distance and stop. But if you want the ball to keep rolling with the same speed, you'll need to keep pushing it. Okay, something similar here also. Right. Now see, the situation, like whatever we are talking about here is outer space, no gravity. We are applying a force, but still the velocity remains 5 meters per second. Like to maintain the speed, we need to apply a force. Now Newton's first law says, if net force is acting, if a net non-zero force acts on a system, its state of motion should change. But now, to maintain the state of motion, we are having to apply a force. Is this contradicting first law, or is there something we are missing here? Is there something we are overlooking here? Okay. So see, basically what is happening here is, as Pawan said, when the block moves forward, its mass increases. Mass gets accumulated on the block. The dust particles sit on it, okay, get stuck to it. So mass of the system is increasing. You want to maintain the same velocity, but the system's mass is increasing, then also it requires a force. Okay, so see, the basic discussion we are having is how to find out if the state of a state of motion of a system is changing or not. That is what we were talking about. Vanilla said if its velocity changes, then we can say that state of motion has changed. That is one thing on which the state of motion depends. Another thing on which it depends is the mass also. Without velocity change, even if mass is changing, you will say the state of motion has changed. Okay, so effectively, what I mean to say is state of motion of a system, of an object or a system, you can comment on it or you can tell whether it has changed or not, depending on a quantity which includes both mass and velocity. And which is the quantity which includes both mass and velocity?
Momentum, sir.
Momentum. Okay. So based on momentum, you can tell whether the state of motion of a system is changing or not. Now, what does the first law state? First law states that state of motion continues to be the same unless a net force acts on it, or reverse. If net force acts on a system, state of motion changes. Means there must be a relation between net force and momentum of the system. Okay, because net force is what affects the state of motion. Means net force affects the momentum of a system. There should be a connection between them, and that is what second law gives you. It relates force to momentum. Okay, I'll just mention it here. It relates force and momentum. So Newton's second law states that the net force, okay, it's actually the reverse. The rate of change of momentum of a system is proportional to the net force acting on the system. So how quickly the momentum of a system changes depends on how much resultant force is acting on that system. That is what is Newton's second law. Let us put this in mathematical form. Can one of you tell me how to mathematically express rate of change of momentum? Okay, this is rate of change of momentum with respect to time. So how do you write that mathematically?
dp by
dp by
dt, sir.
dt.
Correct. Instantaneous rate is dp by dt proportional to net force, and the proportionality constant is 1 itself. So you can say that net force acting on the system itself is the rate of change of its linear momentum. This is what is Newton's second law. Okay. Now, momentum is a quantity which depends on mass as well as velocity. Now, it's quite common to come across systems whose mass remains constant. Okay. Or the variation in mass can be neglected. For example, you take everyday objects, okay, like maybe the mobile phone that you are holding or the computer that you are using. Its mass almost remains the same over time. Okay, unless you remove some parts from it and all, or you add some covers, the mass of the system remains the same, right? So if mass remains constant, if mass is constant, okay, this is a condition, and whatever we are writing, we write after this is valid under this condition only when this condition is satisfied. By definition, we know P is mv. Then net force, that is dp by dt, becomes derivative of mv. And if m is constant, you can put it outside the derivative. You will be left with dv by dt. By definition, what is dv by dt? Rate of change of velocity with respect to time. What do we call it?
Acceleration, sir.
Acceleration. And this becomes ma. Okay. I'm sure you all must have seen this equation, F is equal to ma, but never read it as F equal to ma. Always say F net is equal to ma. And this equation is valid under the condition that mass remains constant. Okay. So we will be, over the next few classes, we'll be solving problems based on this equation. We'll consider some systems whose masses don't change, okay, or systems which involve objects whose masses don't change. And we'll be applying Newton's second law to such systems. Okay, so let's quickly go through what all we discussed today. First, we talked about this quantity momentum. Then, like for a single particle, it is mv. If an entire system of mass m has the same velocity v, then you can say system's momentum is mv itself. But if different parts of the system move with different velocities, then you will have to calculate momentum of individual parts of the system separately and add them. Okay, and by definition, momentum is a vector quantity, so you'll have to add them as vectors. We solved a few problems based on total momentum, change in momentum. Okay, then we talked about impulse. Impulse is change in momentum only, but it should happen suddenly. Abruptly, it should happen. Okay, within a short interval of time. We solved some examples based on that. Then we discussed Newton's first law and second law. So there's a formula for second law. So we will have to solve problems based on it, and it's very, very important. So next class, which will mostly be tomorrow itself, we'll discuss Newton's third law and then apply these to different systems. Okay, fine.